Shah. We are here for the subject Computer Organization and Architecture. In this subject, we have started Unit 1, that is Computer Data Representation and Resistor Transfer and Microoperation. In this unit, we are going to see today the topic that is Resistor Transfer language. Okay, so let me start with the topic. For any digital system, the hardware organization can be specified or defined by three things. First is the resistor it contains and their function. Second is a sequence of microoperation that are performed on binary information that you have stored in this resistor. And third thing is a control that initiates this sequence of microoperation. Okay, so you will require resistor, then you will perform some microoperation on this resistor, and this microoperation will be be in controlled way. Okay, so here we have used a term resistor. What is this resistor? These resistors are generally combination of flip-flop and that contains or that stores your binary information. These resistors are generally designated by a capital letters, or sometimes it is followed by numbers, and that capital letters denotes its function. Generally it denotes its function. For example, if you have a resistor that stores your memory address, then it is represented by MAR, or you can say memory address resistor. Okay, similarly you can use PC for the resistor that contains your program counter, IR for the resistor that contains your instruction register. Okay, and so on. You also can use R1, R2, R3, R4 like capital letters and some numbers. Okay, for example R0 to R50. Okay, so by this way you can represent your resistors, and this resistor can be represented like this R1 with its individual bits like 0th bit, 1th bit, 2nd bit, 3rd bit, and so on. Okay, or you can represent this into a two parts like upper part and lower part. For example, we have PC program counter, and if it is 16 bit, that means 0 to 15 bits. Okay, you can divide it into two part, that is 0 to 7 and 8 to 15th bit. This 0 to 7 bit represents your lower part, that is PC low, and 8 to 15 represents higher part, or you can say upper part, PC H. Okay, so you can access this resistor by its whole, or you can say like R1, R2, R3. You can also access by its bit like R1 zeros resistors 0th bit. We will represent this in terms of parenthesis. We will see next. Or you can access it by its upper portion and lower portion like PCH, PCL, and so on. Okay, so next thing we will require is a microoperation. Okay, so as we know that for any digital module we can define it by a resistor that contains and microoperation that perform on this data. Okay, so these operations are executed on data that stored in resistor that is known as a microoperation. Okay, so these are elementary operation that perform on the information that you have stored in one resistor, and the result of this operation may be replaced into previous binary information, or you can say in the same resistor, or if required then it can be transferred into another resistor. And this operation can be shifting, counting, clearing, loading some content into resistor. Okay, so this will be a basic operation that you are going to perform on these content of this resistor, and that is known as a microoperation. Simply we are doing any operation, we will see it as an operation, addition operation, subtraction operation. But whenever you are going to perform this operation on the content of resistor, then we will see it as a microoperation. Okay, so let me see further as a resistor transfer language. The symbolic notification used to describe this microoperation transfer among resistor is known as a resistor transfer language. Here we have used the term resistor transfer to implies the availability of the hardware logic that can perform the stated microoperation, and the transfer the result of this operation to the same or another resistor. Okay, and this word language, it is borrowed from the programmer which applies to the term of programming language. Okay, and the resistor transfer language is a system for expressing in symbolic form of micro operation sequence among the register of digital model. Okay, so in resistor transfer language we are going to represent this micro operation. Okay, so it is the language of micro operation. Let we will see how you can represent this by simple one example, that is resistor transfer. If we want to transfer the content of one resistor to another resistor, okay, and that is represented by the terms of resistor transfer, or you can say for this operation we are going to use this transfer operation, that is by represented by this arrow. If we see this statement like R1 given R2. So this denotes that the content of R1 is going to be stored into resistor R2. Here R1 and R2 are resistors. Okay. So the content of this resistor R1 is going to be stored into resistor R2. Here the operation is performed on bits. Bitwise operation will be there like this. If your content of resistor R1 is like 1101 and content of resistor R2 is after this shifting operation, this content of resistor R2 will be 1101 bitwise shifted at the same position bits in resistor R2. Okay, here after this operation the content of resistor R2 is going to be changed, but content of resistor R1 will remain as it is. It will not going to be changed. Okay, but the content of resistor R2 is going to be changed. So this is the transfer operation, or you can say transfer micro operation of transferring the content from resistor R1 to R2. Okay, but here we do not use any condition. We have randomly told to transfer the content of resistor R1 to R2. But if you require to transfer, to take this transfer conditionally, like this example, if your condition is, some condition is P, if your condition is fulfilled, that means your output of that condition will be 1, then and only then you have to transfer this content of resistor R1 to R2. Okay, so your statement will be like, if P is equals to 1, then R1 transfer to R2. Okay, so in terms of this micro operation, or you can say RTL language, you have to write like this: P then colon R2, R1 given R2. That is, the content of resistor R1 is going to be stored into R2 only and only if P is 1. If your condition is like that, if P is 0, then and only then you have to transfer this. Then you have to write here P dash. So your condition will be P dash. If P is 0, then this transfer will take place. Okay. And by graphical way, we can represent it like this. It is your control unit that generates your P signal, and that is used for this controlling the content into resistor R2, or you can say loading some content into R2. This connection of R1 and R2 is done. Okay, but this content of R1 is not transferred to resistor R2 unless and until your P is 1. Okay, so when you got this load signal, or that means your P is 1, so at that time your transfer will take place. If it is 1, then you got rising age of clock, as your all of your task in digital system completes on clock. So whenever you got the P bit as a 1 and rising age of your clock, that means you require to complete this task. Okay, so this transfer will take place over here. Okay, so by this way you can conditionally transfer the content of one resistor to another resistor. Okay, there is another symbols also that you can use here, that is list of that symbols. As we already know that you can use letter for your resistors, parenthesis for representing your bits. For example, if you want to represent your 0th bit, 1th bit of resistor R2, then you have to use R2 in bracket 0, R2 in bracket 7, whatever your number. And if you represent lower part or upper part, then R2L, R2H, and so on. For any resistor you can use. Okay, then arrows represents your transfer operation. Okay, one another operator you are going to use, this is comma. That comma is used to combine two microoperation at one clock. For example, if you want to transfer the content of resistor R1 into R2, and at the same time you want to transfer the content of resistor R2 to R1, so for that case you have to use this comma operator. So at one clock you can use comma operator and complete more tasks at the same time. Okay, so these are the basic symbol that we are going to use for resistor transfer language. Okay, letters, parentheses, arrows, and commas, and each and every symbols has its equal meaning. Okay, so we are ending our today's session over here. If you have any query, then you can contact me or write in a comment box. I will try to solve your query as soon as possible.